Okay, let's now look at the implicit differentiation. Okay, so it's a method, it's one separate good method to learn how to take derivative. Okay. So we've learned from previous lectures that the term differentiation means the process to take the derivative, right? So here implicit differentiation is sort of like a one specific technique right here that handles quite a few situations out there. Handle like taking the derivative. So I keep reminding you about the use of the dy dx notation right here. Okay. So this Leibniz notation for taking derivative, it has a specific meaning that yes, this is the derivative, but it came from, you see the dy here means we're treating the y variable, right, as the function. And the x here is being targeted as the independent, okay? Independent, or a lot of time I call it the main variable. They're all variables, but there's one being the dependence variable and one being the independence variable. Okay? And then so I've been saying that, but this is where we starting to see that's like really clear right here. Okay? So why do I have to keep mentioning, you know, so among two variables, one of them is the independent and one of them is the dependent. So the example comes right here. Let's say now it's just simply out of nowhere you are given an equation like an x squared plus y squared equals 4, for example. Okay? So it's an equation that got two variables involved and all that, right? Two variables involved here. So now, right from this equation, and by the way, you guys are calculus level now. You guys recognize what the equation that is? What kind of graph does this equation give? It's a circle. Okay? Get into a habit. When you say a circle, where's the center for this equation? Any circle got a center and a radius, right? So when you read the equation of a circle, what's the center information of this circle? 0, 0. Okay, I agree. Okay, where's the radius? 2. Okay. Yeah, very good. So it's a circle. So according to your information, it's a circle. Center at 0, 0 in the origin. That's the center, and then the radius being as large as 2. Yes. See what I'm saying, no? Okay. And so for the equation like this, think about it. Right now in the way how I'm seeing it's simply or purely it's just an equation, right? X and y are related. The two variables here are related. But so now let me ask you this next question right here. Who among these is a function? See what I'm saying now? There's the x variable, right? There's the y variable. See what I'm saying now? Who among the two guys here, who among the two variables here is going to be the function? So the truth now is that any one of them here can be a function. Any one of them can be the function. It all depends on what we want to work with. So think about it. So the truth here, like I said, anyone, right? Anyone of x, right, or y can be the function. See what I mean? Because so here's the thing. Think about if you make your choice. If you want x, right? If you want x as the function. Okay? If you want x as a function, then think about it. The same equation right here, you can do the following. X squared plus y squared equals 4, right? Then what do we do? Well, from your algebra classes, we can subtract x squared from both sides. You guys agree? Okay? That's making it y squared equals 4 minus x squared. You guys see what I'm doing then? Okay? My point now is that you see where I'm going. If we have decided to make y as a function right here, then we're on our way to solve for y as one single variable, right? And the opposite side is just a whole complete expression in terms of x. So taking square root both sides is going to give me, now be careful a little bit here. When you take the square root here, we have to run into the 2 square root here, right? And I will get back a little more detail into that, but the truth now is treating y as a function, we have to go, yes, we solve for y, right, as a function right here. And then we end up with plus or minus square root of 4 minus x squared. And And just like I said earlier, there are going to be a lot more details than just that. But right now, I'm just pointing out for you that, hey, between the two variables, any one of these two variables here can be the function. But once you have decided solve, right, you've got to solve for that one, yeah, as a function in terms of the other one. See what I mean? So just like that, any one of these guys can be the function. So you can also decide to make x as a function. It's all our decision right here. So if we want to do so, then how do we get x as a function? Because right now these two, in other words, saying these two variables, they're sort of like standing in line. See what I'm saying? They're standing together on one side, or they have about just their own equal role right there. Just being related, that's all. So now if we intentionally want to make x as a function right here, then we got to solve for it. So x squared plus y squared equals 4. Again, I'm subtracting y squared on both sides this time, right? And you guys should be comfortable with doing this kind of algebra work, right? Solving for one variable in terms of the other one. And so here, right, I have x squared, right, equals 4 minus y squared, and the very similar work comes out here. Solving for x, we take the square root of both sides, right? But don't forget, we've got plus and minus square roots here. You guys following? And then there's y squared minus 4. Right? If we decided to make x as the main function, as the function, and then that means what? In this case, the x is the function, and the y right here is the variable, the independent variable. So you guys see what I'm doing now? Okay. So now we take that idea. So back to the bottom line, I was saying that right here, any one of the two variables here can be the function. It all depends on how we want to make it. So here's the thing. What if we want to find the derivative? We want to find the slope of the tangent line. Think about, see, this equation here has a graph, right? Being a nice curvy graph right here. So we can technically place a tangent line anywhere on that graph. Am I correct? Right? And for that reason, the slope of the tangent line is going to be done by finding the dy dx, right? The derivative. You guys follow me on that together? Okay, and so now the big challenge, once again, let's say I give a challenge like, hey, right at that point, and you guys already stated out to me, this equation right here has that famous, it's a circle set up 0, 0 with the radius 2, right? So how about right at that point, 2, square root 2, 2 right here. You can quickly check that this point stays right on the circle, right? The square root 2 all square plus another square root 2 all square should be equal to all 4, right? You guys agree with me on that figure? So think about, hey, right at square root 2, we're at 2, comma 2, comma square root 2. We want a tangent line like that, right? What's the equation of that tangent line? See what I'm saying, no? So same rule. The equation of that tangent line is y equals some slope mtx plus b. You guys with me on that now? Okay. And so in that way, yes, we need to get the slope. The first thing we need, right? See, so right back to this equation right here, we want to find the dy dx. That's because the biggest goal right here is to get the equation of the tangent line, and we are going to place at the square root 2, comma square root 2. Right? But to get that equation right there, yes, we need the slope. Right? And in order to find the slope, we've got to start out by finding the derivative of the function. Are we good with that right there? You guys all caught up, taking note with that so far? And so now, I explained a lot, I mentioned a lot, but now in the end, think about let's just even forget about the picture of the graph, the tangent line as the goal right here. Let's just forget about that. Just think about at the simplest level, out of nowhere, you are given an equation, right? An equation with two variables. Any one of them can be the function, and then the other guys being the variable. And then out of that equation, you're just simply being asked to, hey, find the dy dx, right? And like I said, let's completely ignore about the biggest goal to find the equation of tangent line. So think about from an equation like this, and you are instructed to find the dy dx. Your first thing you need to do is to read the symbol over here. This is where, once again, the symbol has a tremendous indication. Because I've been saying, now, in this equation, any one of these can be the function, right? And once we have chosen a function, the other guy is going to be the main variable, the independent variable. So in this indication now, the problem, once it's instructed, right? When it's giving you the instruction, it gives you a clear, based on that symbol, it gives you a clear indication now from this equation who we want to be the function and who we want to be the independent variable. You guys see what I'm saying now? So in this case right here, who's going to be the function according to this intention right here? We want y, right, as the function, and we want x, right, as the independence, right? Or a lot of time I also refer to that as the main variable. Right? Just like, once again, just the way how the problem was given out, right? The instruction that the problem gave out right there, it led us into that decision that, hey, we're gonna have to treat y from this equation, right, being the function, and the x being the variable. You guys still together with me? Okay. But so now, taking account for this, right? Taking this understanding now, after taking along with this decision, but still, what I did earlier, the little bit scratch what I did on the board here was completely unnecessary. I was just trying to point out for you that any one of the x and y can be the function. The work I did right here. So deciding y as a function, right? We're gonna subtract x squared from both sides. You guys following? Right? And then we go, that becomes y squared, right? 2 equals 4 minus x squared, and then the y equals the plus and minus right here. Let me tell you the truth now. Yes, even though we're intending that y is a function and x is the variable, we still don't want to do this route right here, because an equation like this is right now is still okay to solve for y. See what I'm saying now? But what happens if you have like a cubic and things are even more crazy involved again? Are you following what I'm trying to say? So we just know that tentatively y will be the function and x will be the variable, but we don't want to solve it explicitly, because solving it out like this is called the explicit form. Okay? The explicit expression, because it's showing things out. Right? So if we can finally solve for that, we call it as the explicit expression. But we don't want that way. We don't want to go that route, because solving, like I said, solving for an explicit expression is a lot of time challenging, really challenging. Right now, this thing is still easy. It involves only the basic operation. But solving it a lot of time can be challenging. So we want to go directly. We want to just directly find the derivative. So now we gave up solving explicitly, right, for the expression. So we just now think that, hey, yes, we know that y is a function of x, but it's just it's there, but we're just not having the explicitly the show down the form of that. So I call it as y is the implicit function, right, of x. And as a matter of fact, y equals, right, some implicit function of x. Are you seeing the term implicit right there? It means the function will be there. The function is there. It's just we don't need to show the expression. Right? It's kind of hidden there. It's hidden inside of that equation. That's why I'm using that term implicit. You know what I'm saying? No? Right? So y is just some function of x, but we just don't need to know. We don't need to know the particular expression of that. Right? So that's so for this one we're starting. So I'm going as low as I could, because for you guys to identify the challenge. And then another quick note here. So y being some implicit function, right? Then that means just think about it. It's going to be some y is equal to some f in terms of x, right? That we didn't know what it is. See what I'm saying? Now, if we could have solved that and solved it down, then yes, we had a formula, but now we're keeping that completely implicit. And so in that way over here, we just, yes, it's some function f of x, but we don't have to know what it is. And so back to this equation, it kind of means, right? Think about your mind process. The equation will reduce down to x squared plus, right? And some f of x that we implicitly hiding that with the y variable, right? All squared. You guys follow me on that, okay? And equal to 4 on the other side. Right? Like keep in mind, this is just some implicit expression of x that we didn't bother finding. That's why I'm leaving that some kind of fx there. Okay? So that's just some reminder in your thought process. Okay? By the way, this is a plus sign. Okay? Looking from afar, it kind of looks like a T symbol. Okay, so now after all of those beating around the bush information, which hopefully is important for you to catch, then we got the clear method to do it. So starting with the x squared plus y squared equals 4. I want to take the derivative directly. So now here's how I'm applying the symbol. Right from the equation, the first step is I'm going to apply that dx. You guys see that the way how I use it, right? The d symbol, right? Over dx right here means it's an indication that we're going to take the derivative. It's an indication of the process. Hey, let's differentiate this two terms thing, right? In respect to x, meaning we treat the x as a variable. You guys follow it? Okay? So I'm doing that. If I'm doing that on the left side, I'm doing the same for the right-hand side, taking x as the main variable. You guys follow with my verbal explanation on that? That's how I'm applying this operator, right? So I introduced that a little while ago, but we didn't have direct use until kind of like now. We good with that so far? Okay. And so, well, let's handle from the easy side up. It's just a constant on the right-hand side, right? So no matter what variable that we are differentiating in respect to, it's going to go out to be a 0. You guys follow it? Okay. So on the right-hand side, come out just a straight old 0. No need to doubt about this, right? Basic derivative rules, all of those universal rules we've learned carry in here. We've got two terms, you guys agree? Okay, two terms, so we can do one separate derivative. We can take one separate derivative process on the x squared term, right? And we take one separate derivative process, okay, on the y squared term. You guys follow it? So just the familiar rules that we've been looking through, right? And at this point of the quarter, you guys have seen all of those, right? I'm just applying those in. Okay. So now, once again, it makes natural sense that this thing is a little icky right here, so I'm going to get back and explain that, but this one here is easy. Our term is just simply a what? An x squared term, right? And we want to differentiate, we want to take the derivative in terms of x. So the derivative will come out as easy as just what? 2x IB. Sounds good. Okay. The other term right here, I will get back and explain. Okay. But the way how it looks for now, equal to 0. Right? So sum 2x, right? The derivative of the first term, because the first term was completely expression of x, and we're taking the derivative in respect to x. You guys are still with me? Right? But then, so now let's look at some explanation for this. I have mentioned that earlier on the other board right there. That's why the line was a little kind of important. So implicitly, this is just in your thought process right here. I don't need you to write this down. Okay, but I mean, right now you take note and you do whatever. Try to think about in your written word right here. You don't have to tell people this. So implicitly, the way how I see it is y is, remember, some function of x, right? Some function that we didn't know. Remember, we don't even think about solving for y to be equal to positive or negative square root or whatsoever. Just give it up. Are you following what I'm saying now? Yes? Technically we can do that, but we gave it up. We didn't want to go that way. So implicitly y is some function of x, right? And so now that means what? In our equation we got y squared, right? Y squared has to be what? F of x all squared. You guys follow it? Okay? And so that means what? Further, the work here is asking us, hey, differentiating the y squared here. This is important. We apply the operator, differentiate, take the derivative of y squared means that we're taking the derivative of this f of x squared. You guys following? Are you seeing what I'm explaining right now? And so in that way, what have we just learned recently? The chain rule, right? There's outer function being the square, there's the inner function being some unknown function. Okay, you guys following? But some function of x. You guys following that? My purpose is, once again, I keep reminding you that y is playing in the role of some implicit function of x. So think about, hey, there was some expression of x that we didn't know, right? That's what represents y. And so y squared means the entire implicit expression there being squared, right? The entire implicit expression of x being squared. So taking the derivative of that, so seeing the whole thing now as in terms of x, we just don't know what exactly that expression is. So taking the derivative with respect to x, right? It gives me what chain rule says, outer function, right? That's the outer. So we got a master with the chain rule as well, right? The outside function, and there's your implicit inside here. The outside is being some squaring function, right? And the implicit is the inside one. And so chain rule says, taking this derivative, it goes 2 times the f of x. You guys will need that. Right? And this is everything here is on scratch where I didn't put it in four more steps like that. And then with power reduced by 1, that's making it power 1. Right? We multiply with the derivative of the inside. Sounds good? Did we know what the inside is ever? We've never ever known, right? Because remember, we decided to keep that implicit. Right? We have decided to keep that y being implicit without the need of worrying about what exactly that is. So now that means what? Without knowing it, all we can do is leave that as some implicit derivative f prime of x. You guys follow? The derivative of the inside, right? But now let's put it all into one big picture. It means what? This f of x in the end, yes, the shorter variable name for that is a y, right? So I'm looking at a 2y, you guys seeing that there? And the f prime of x here is just the implicit dy dx, right? After working out my process with that. And so really in the formal written steps, right? So right from here, the next step, 2x from the early term is here, right? With this operator of taking the derivative of the y squared term means, see, it's going to give me 2y, right? Times dy dx equals 0. And I really mean it. It was a chain rule that gives me 2y times, right? The dy dx, the implicit dy dx. It's some derivative existing out there. We just don't know what that is. We keep it as implicit as well. Okay. And so now, but we're still not done. I just now finished explaining how I came from here to that, right? And I hope you got all of that, the mind process, the way how it works, right? But really, no one's requiring you to write down all of these explanations right here. See what I'm saying now? So that's just for you to understand. So right from that, keep in mind our goal is to find dy dx. See, our goal is right here, is to find dy dx. We're getting closer. Right now, what we ended up with was that 2x plus 2y times dy dx equals 0. So what we have here is an equation that involves the derivative, right? So right from that equation, allow me to rewrite it here. Right? 2x plus 2y times dy dx equals 0. I can subtract 2x from both sides, can I? Right? It's an equation, right? This is a variable, that's another variable as well. See what I'm saying now? Okay, so I'm subtracting 2x from both sides, I'm ending up with a 2y times the dy dx equals minus 2x. You guys will be there still? Okay. And now I'm going to divide both sides by 2y. Okay? It's all the algebra after that step. And this step was the most important one. Okay? Because we found the derivative implicitly. And now at the end here, I'm on my way to just algebraically solve for dy dx. You follow me on that together? Now we have a final expression of dy dx. One final dy dx stands on its own. The right-hand side now is a minus 2x over 2y. You guys follow it? Okay? And then of course your algebra here allows you to cancel out the 2, right? Making it really minus x over y. So we have come to the final derivative. Y dx is concluded to be minus x over y. You guys saw the technique, no? Okay. I hope so. You guys did. Okay, so go ahead and put that in a box. It looks a little weird, doesn't it? But what's the weird thing? I hope you guys see the same weird thing as I do. Yeah.
There was both x and y.
Yeah. See, just last lecture, right? By the end of last lecture right there, every derivative we found at the end was only just in terms of x, as a function of x. See what now? All of a sudden now our derivative, we're starting to take, there's a y in here. See what I'm saying? Now, that's the weird thing that a lot of times when we first learning about it, we feel weird. But let me tell you again, remember that your y here is some implicit function of x. Some implicit function of x. So what it says here is that, hey, the final derivative is just generally telling you that whatever your y can be solved for, right? Whatever your y can be solved for, it's just simply minus x over that implicit function of x. That implicit function of x that we never had to worry about. You know what I'm saying? No? For example, you know, really, let's go through some big work here. Let's say if we really have to solve for it, okay? Like I said, we gave it up. And a big amount of times we don't want to solve for y in terms of x because we try to avoid doing that, right? But for the purpose to convince you about this, let's really go ahead and solve for y. Yes, the familiar word comes back again, right? Subtracting x squared from both sides of the equation. That leads to y squared equals 4 minus x squared. You guys would be there, okay? And then we're gonna have. This is really this really point here. When you solve for this thing, there's that little secret that I didn't mention that I was hiding before. I mean, we got there, but I was holding on to those details again. Remember that we solved for that. We actually ended up with plus or minus square root of 4 minus x squared again. Remember that point? So here's the truth. As far as seeing y as a function of x, there are actually two different ways. See what I'm saying? There are two different functions. You actually have solved for one function, y equals the positive square root of 4 minus x squared. And you also have another function, y equals minus square root of 4 minus x squared. It's not just like one function of y. It's not like y equals one function of x. It's just the same letter, y equals two separate functions of x. Two separate functions. Look right on the curve here. The curve itself is a circle, isn't it? So this circle is nowhere considered as a function. Remember from pre-calculus 1 right there? Because the vertical line test says this entire graph fails, right? One x value crosses the graph at two y values. That's why this whole graph right here is not considered as a function. But then we purposely, what's up with the equal positive square root of 4x squared? Positive square root of 4x squared means you can take the upper dome right here being a function. So now if you just chop it up into one upper semicircle, that is a function of x. This curve right here is the y equals square root of 4 minus x squared. Are you following my arguments again? And then the other guy, what's up with the negative square root of 4 minus x squared? It's the guy in the bottom side right here. See what I'm saying now? And the two functions come together to stick together, it makes the one complete circle right there. That's why as an equation we read one equation x squared plus y squared equals 4. But if separating it down to functions, we're talking about y has to be two different functions. Okay? One function is this guy and the other function. And I don't know how I made that bottom curve so bad. Okay. But anyway. So think about it like this. The work may become a little big right here. In your experience, up to this point, I'm just trying to explain for you this general concept about why are we having a y in there. Just think about it. If you chose your y, okay, if you chose your y equals square root of 4 minus x squared, that means that you can rewrite this algebraically as a 4 minus x squared to the 1/2 power. You guys agree? Okay. That means that when you take the derivative, okay, this route now is explicit route. Am I correct? Because we have. I'm saying if we already found the explicit expression of that, then the derivative comes down 1/2. Okay, 4 minus x squared raised to the power 1/2 minus 1 being the negative 1/2. You guys agree still? Okay. And we multiply with the derivative of the inside here, giving me minus 2x, right? So the derivative is here, canceling out the 2, and then we're making it minus x times the 4 minus x squared to the negative 1/2 power, right? And I've been going a little loose about, I've been going a little easy about, or flexible about letting you guys all be okay with the expression of negative fraction. But the truth now is that you can rewrite this as a minus x, right? All over the square root of 4 minus x squared. You guys repeat that? Okay. Do you see that it's minus x over, this is your y there? So if we decide y to be the positive square root of 4 minus x squared, right? The final derivative is going to be coming out minus x over that y anyways, right? And then think again, right here from that scenario, even if you chose, right? Even if you chose that y to be minus, right? Yes, you can rewrite that as, it's a different function now. But in either scenario, minus 4 minus x squared to the 1/2 power, you guys with me still? Taking the derivative, what dx gives me, so I keep them in the negative sign because that's -1, right? Coefficient. We multiply the 1/2 down. Okay? 4 minus x squared, according to chain rules, yes, the power, the derivative of the outside function, so that's making it now power to the -1/2, right? We multiply with the minus 2x, derivative of the inside the result of this. And now, let's cancel out. So with the positive side, I mean negative, with the negative cancel out, making it positive, the 2 cancel with the 2. So that's going to be positive x, right? Times 4 minus x squared to the -1/2 power. Okay? So that means we can rewrite it as x over positive square root of 4 minus x squared. But here's the thing, let me purposely, the clean answer is this, but let me purposely do this. I want to purposely make that a negative here and a negative here. I mean, it was supposed to be a positive x over all that square root, but I purposely put that a negative here and a negative here. And don't cancel that, because you see why? Because now, think about it, even if you chose y equals a negative square root of x, right? Even if we spent out so much effort solving for that and decided, hey, y equals negative square root, the answer still come out minus x, right? Over, why do I put the minus sign here? Because that's still your y right there. So either way that you're solving, right? Either way that you're solving for your y, if you decided to spend so much time solving for your y explicitly right then, you're still going to end up with the short form. This short form here minus x over y. That's why the implicit route is a lot more generalized right there, right? And it includes, it's a lot more inclusive. Are you following my explanation right here? So please, you're not required to do this. I'm just trying to convince you that, and to give that explanation of, why there's such an equivalent y variable there. It means, it doesn't matter how you solve for y, right? It's still going to be there in the denominator. Solving for y is just simply going to make it more explicit, but we a lot of time not required in this kind of work. That's the idea. All right, so we found the derivative. Back to the big goal of the problem right here. That means all of a sudden narrow your attention down to so much implicit differentiation, right? But remember, the biggest goal is, hey, how about right at that given point, square root 2 comma square root 2, right? On this circle right here, we want to find the equation of a tangent line, right? So we already found the derivative. So the derivative now came out at this point, right? The derivative is a minus x over y. You guys following? Okay. So that means what? Do we now have direct access to get the slope of the tangent line? What makes most natural sense for you guys? How do we find the tangent line, the slope of the tangent line here? You already have the derivative being the minus x over y. Yes?
Just substitute.
Yeah, substitute the complete pair, right? You can see that now the tangent point is given as a complete pair of values again. You guys following? So what makes most natural sense for us is substitute that. So x for x and y for y, right? We're substituting that into our derivative that's supposedly having a lot of y's involved as well, right? So minus square root 2 for x, right? Over square root 2 for y. That's how we substitute it in. So the slope of the tangent line comes out being what? -1. Right? So that means now, so we got the slope, so that means our tangent line at this point is halfway completed, right? Supposedly y equals minus x plus b. Does it look at least consistent with my picture right there? Of course, my picture is off scale all over it, right? And I'm not even sure if I put that point there exactly at the square 2 comma square root 2. That's not the point, but even if it's still a little slightly off. Putting the tension there in that position has to make it what? A negative slope line like that. That's why I see it's consistent. You guys following? Right. Have we found a tension point? Well, we didn't need to find it, right? It was already there. So what's our tension point? Once again, let's just repeat that, right? The next big step like that, right? Square root 2, comma square root 2. You guys following? Okay. So now how do we get to that complete equation by solving for the b right here? Just need to substitute this point, not into the derivative, right? The derivative has already given us that slope. So now we're going to substitute this tension point again into the halfway completed tangent equation like that, right? That's making it square root of 2 equals negative 1 times the square root of 2, right? And then plus b. And so to solve for b right here, that means what? B here, we add that to the square root of 2 to the other side, right? Making it now really 2 square root of 2. Final equation now, yes, this point right, this line right here, yes, the final equation y equals minus x, right? Plus 2 square root of 2. Right? Yes, I understand completely that we're not very comfortable looking at these m and b values being irrational like that, but it happens. It does happen quite sometimes. Right? So getting the complete equation is a big goal, but the biggest part in that work was to find the derivative. And so that's where I got to introduce this technique right here is to find the implicit differentiation. You know what I'm saying? And remember that even back to the, see, how do I know to take how do I know to treat y as a function and x as the variable? It goes back to this beginning instruction right here. That we were given the problem, hey, let's, from this equation, let's find dy dx. So in your role right here, you understand, reading that notation, you understand that, hey, y has to be, y was already decided, right, by the symbol right here, that y is a function, is the function. And then the x here in this equation is going to be the independent variable. You guys are getting the big idea of that problem right there? So now think about it. Let's roll back to that point when the equation was given out. And I was saying, so back to that point, the equation was given out, and I was saying, any one of the two variables, the x can be the function, right, and the y can be the function. So in the problem I just now erased right there, then you were asked to find the dy dx, and that dy dx gives you a clear instruction that, hey, the notation indicated for us that y is chosen as a function and x is chosen as the variable, right? But still, that means there still could be a possibility that you are asked to find the dx dy. You see what I'm saying now? Because out of the two variables, right, in that same equation, any one of the two variables can be a function. So it makes perfect sense that yes, someone can give you an instruction, hey, let's find the dx dy, meaning now we want to treat what? Who's the variable and who's the function this time? This guy is the function. You see what I'm saying? Now this symbol right there, the way how the problem is instructed. Okay? So the dx dy now we will intend that x, right, as the function in the role of the function. You see the difference in the symbol right there? It tells you a lot. And then the y right here in that from that dy, right? Y is regarded as the independent, right? Independent, or a lot of times I tend to call it the main variable. See it now? Okay, so let's find the dx dy here. Keep in mind that our x will be the function this time, right? And clearly we don't want to solve for x in terms of y anymore. We just directly giving it up because we want to keep the x completely implicit. You guys following? Right? So just know that x is some function of y that we don't have to know. That's all we need. Keep in mind. So starting back to that, getting back to that starting point, x squared plus y squared, right, equals 4. You guys all following? Okay, I wrote it with so much space out for a reason, for a purpose. Okay, but now I'm gonna differentiate, right? I'm gonna apply that d operator, but this time, what do I put down here? The dy this time. You guys see that? Right? I'm gonna take the derivative of this two terms thingy, right, in respect to y, treating y as the variable, as the main variable, and x is the function intended. Right? So now I'm differentiating 4 here in respect to y as well. So in that very same experience you have seen from the earlier demonstration, then no matter what that variable is, the constant here is going to go to 0 after you take the derivative, right? Okay, so the derivative of 4 here is 0. You guys all good? Right? And then the universal basic rules, I mean the universal derivative rules allow you to separate it out into two separate terms, right? We can find one separate derivative, right? One separate derivative for the x squared, right? Plus one separate derivative in terms of y for the y squared term. So once again, when it comes to this point here, you can see that we are instructed to calculate the derivative in respect to y, and our term here is already in terms of y, right? This is an explicit expression in terms of y, so the answer comes out as easy as just 2y this time. You guys see that? So kind of like as a quick checking point for anyone that anytime the d expression right here, right, the d notation has the bottom variable agrees with your variable in the expression you're doing, then that's easy, right? That's just the usual work again. So like a y squared, you're asking to indicate, I mean to differentiate in terms of y, and it's just simply y squared. Nothing icky, nothing bad about that. This is where it's becoming challenging for us this time. D, dy, dx squared. Right? So let's hold on to that. I only explained by far, how easy that is just to get the 2y this time. And so once again, let me come back with a lot of explanations here. But x is some implicit function of y. So our equation here has the x squared term. Right? X squared is being involved in our equation. So x squared means what? You've got some f of y implicitly defined. And square that. So now differentiating, right? Taking the derivative of the x squared term, right, in respect to y, it means we're taking the derivative of this whole f of y squared, but differentiating all of that in respect to y. See it now? And this is where, once again, we have to apply the chain rule, right? The chain rule says, hey, there's an outer function being a squaring function, right? The outer function being a squaring function. So taking the derivative now gives me 2 times whatever inside we keep the same. That's why I'm leaving the f of y here, right? And then the power here we use by 1. So that's everything here is just the derivative of the outer function. And we multiply with the derivative inside, but we didn't have an implicit, we didn't have an explicit expression of that. Everything is just going completely implicitly. So here we have to leave that as f prime of y, right? So in the way how I'm seeing that now, f of y here is simply just the x. You see, I keep mistakenly saying x a lot of times again because it's a habit that we always have to use x as the variable and y being the function, but not always. This is starting to break you away from that habit again. It may take long. It's still, that habit's still around with me. See, this is 2x now, right? Times the dx, dy. You guys repeat that? And so back to the equation, we actually ended up with the first term here, 2x, right, times the dx and dy. That's how I'm seeing it, right? Plus 2y equals 0. And then from that point on, now all of the thought process and the explanation now, let me clear that out because we need to move on to the next step. Or we need to just fit it into this narrow space right here. So 2x, right? Dx dy plus 2y, right, equals 0. Now I can subtract both sides by 2y. The usual word comes out. Now we solve for the derivative explicitly. So 2x times dx dy equals minus 2y. Right? And solving for the dx dy, we have to divide both sides by 2x. Right? So that gives me dx dy equals minus the y over x this time. But still, your answer must involve the 2 variables in it. You guys can repeat that? Your answer involves 2 variables in it. There's your dx dy that we counted. Right? All right, so ready for getting in? Okay, so the idea of implicit differentiation we already learned, right? So up to this point now, so in this example right here, I designed for that. So the equation we are given here, it's got x and y standing all over, and we're unsure who's going to be the function, who's going to be the main variable, right? Because x could be the function and or y could be the function, and then the other one being the independent variable. That's why for a problem like this, let's find dy dx, and then when we're done with that, we also find dx dy, because any one of those can be the function, right? So let's start out with dy dx first. Well, we know by heart that we can always put a square root as a 1/2 power, right? So let's rewrite the equation x to the 1/2 power, right? Plus 3 constant term equals a y squared. But now on our way to calculate the dy dx. So keep in mind on the scratch work, again, as a reminder, dy dx means the y in the numerator, the y on top of our symbol, it means we're treating y as the function. Okay? And the x in the denominator, this is the x as the main variable, right? Or the independence variable. That's what to keep in mind again. So that means now, yes, I am going to apply the differentiating operator. Right? We're differentiating in terms of x. Okay, we take the derivative in terms of x. In that way, here's how I'm seeing it. See, the left-hand side this time is a little easier. So I'm leaving the right-hand side here for now. Differentiating the y squared. Right? The left-hand side, we can basic derivative rules, right? The universal rules allow us to do 2 separate derivatives, one on the x to the 1/2 power. So that means we're differentiating, okay, the x to the 1/2 power plus the derivative that comes out from differentiating 3. I'm going to leave that here as a reminder. So in the next step, yes, we're differentiating in respect to x, meaning we treat the x as the main variable, right? And the expression is already explicitly in terms of x. So that's easy, right? That one right there, just the first term comes out, the power rule, making it 1/2 times x raised to the power 1/2 minus 1. You guys with me there? And eventually it's going to be a power negative 1/2, right? Plus, now what's the derivative for a constant term? Doesn't matter what variable it is, but it's going to be 0. Right? Plus a 0 equals. So now let's handle that derivative on the right hand side. See, so I have explained this quite a few times in the earlier part of the lecture over here. So we got think about y as some f of x implicitly defined. That we didn't need to know the exact formula. But so y squared here means you got whatever f of x is implicitly defined, right? We're gonna square that. See what I'm saying there? So we got outer function, right? And the inner function is some unknown function, f of x, some implicit function, f of x. And so now taking the derivative in respect to x, right? And that means we take the prime of this thing. You guys remember? So now I just pointed out there's the outer and there's the inner, right? So we're gonna have to bring in the chain rule for that. So the chain rule says it's gonna become what? See, it's gonna become, think about taking that derivative. Right? It's gonna be 2, right, times the whatever the f of x is, right? Power will go by 1 and we multiply with the derivative of the inside, which is f prime of x. And that's how I'm doing that here. It's 2y, because y is a shorter way of writing f of x, right? 2y times the dy and dx. Okay? You see how I work on scratch work and I bring that into our formal step, okay? And then one day when you guys are fluent enough with that, then you don't even have to always do that scratch work step. And then this is even just scratch work level right there, right? To explain to ourselves, to explain to our own mind process, in our own thought process, how we got that. Right? But the formal work is we just go from here, right? To that. And so let's clean up the terms a little bit. So that means what? We don't have to write down the 0 right here. We got the 1/2, right? X to the negative 1/2 power. Right? And all of that here equals 2y times the dy dx. Really it was a multiplication. Right? And so now the work is now simple. We're gonna go ahead and solve for the dy dx, right? I'm gonna divide both sides here by 2y. Look at that there. Right? And the 2y's here will cancel, so that leads to, so now I'm looking at the x to the negative 1/2, right? All over a 4y, how's that? You guys following with the algebra right there? That equals the dy dx. So think of that as x to the negative 1/2 over 2, but divided by a 2y there. 1/2, right? X to the negative 1/2 over 2y. This is over 1, 2y over 1. So that means we're making it x over to the negative 1/2 over 2, right, times 1 over 2y. That's why multiplying those two fractions together, right? The reciprocal in the denominator, I mean, we take the reciprocal of that 2y there. So multiplying those together, we're ending up with the x, right, to the negative 1/2, right, all over 4y. That's how I ended up with that. So we found our derivative right here, dy dx. And be watching out that in case you are asked, you may be asked to rewrite an expression without negative power. So you can also write it as a dy dx, right? Equals to just simply a 1 over 4y with the square root of x. That's the same exact expression. We're writing things in, without rational expression, without, the fraction powers, and then without negative powers, right? And so we have to put that as a root, right? And then in the denominator. See what I'm saying? And that's a different way of writing it. So we're not done with part A. Because why? Same equation here. Square root of x plus 3 equals y squared, right? Yes, we can rewrite this as an x to the 1/2 power as usual, right? Plus 3 equals y squared. But now we want to differentiate. We want to find the x dy. You guys see that? The x dy here, right? So we have to apply the differentiating operator, right? But in terms of y, treating y as the main variable. So that means what? In this case here, the x dy that we're looking for, right? We're looking at x as the function. Okay? And the function in terms of y, right? Okay. Main variable. Agree with each other right there? Right, so what? In this case, x is some function of y, right? X will be some function of y. So now, in this case here, the right-hand side is easy, right? It's all, the entire expression is already some function of y. Right? Expressed in terms of y, so differentiating that in respect to y, that's making it as easy as 2y. On the left-hand side here, well, things that we got two terms, right? So let's break it down using the limit rules. I mean the derivative basic law. So we're differentiating in respect to y for the x to the 1/2 power, right? As one separate term, and then we're taking another derivative by differentiating the constant term 3, right? And so once again, constant term is pretty independent with the variable. No matter what variable that is, it's just going to come out with the derivative being 0, right? So in my next step right here, I'm seeing that I will have to eventually differentiate the x to the 1/2 power in respect to y, right? But that term here becomes a 0, right? The right-hand side is simply a 2y already. So now, in that same explanation, my answer for this now is, we'll see that often enough. It's 1/2 x to the negative 1/2, right? But that's just the derivative of the outer function that we multiply with the derivative of the inner inside the function, dx dy, right? And then the 0 term, we don't need to write it down, making it equal to y, the right-hand side. So once again, why is that? See, just like right here, x is some implicitly defined function of y. So x to the 1/2 means the same function here, the same function of y that's implicitly defined here. We raise that to the 1/2 power, right? So there's outer and there's inner being that implicit function. So taking the derivative now, right? Taking the derivative of that in respect to y, right? In respect to y, then we're looking at, see, the outer function says we multiply that. So outer function 1/2, right? And we got f of y, right? To the negative 1/2. That's the derivative of the outside function. And we multiply with the unknown derivative in front of y. And that's why I have, see, this whole 1/2 and f of y to the negative 1/2 together. That gives me that, right? And then the unknown derivative right there is that dx dy. So now we are ready to solve for dx dy specifically. Dx dy can be found by simply dividing both sides by 1/2 x to the negative 1/2 of that, right? Dividing both sides by that 1/2 x to the negative 1/2. So now in this case, my work turns into x dy will come out being 4y x to the positive 1/2 actually. That's how we done. And then we can also express that as dx y before y with square root of x. That's another way of writing it. So that's the answer. And in case anyone is wondering a little bit with the algebra over here to think about, see, 2y over the 1/2 x to the negative 1/2, right? See, the negative right here in the denominator, we can purposely bring that on top, right? And making it so it's 2y right here multiplied with x, but to the positive 1/2 now, over a 1/2. Sounds good? And then the divided by a 1/2 means we're gonna have 2y right, times x to the positive 1/2 multiplied with a 2 over 1. And that's how I ended up with a 4 here. Right? And that's y to the 1/2. It's all the algebra after that. So really, I mean, if anyone is feeling shaky at any point with the algebra, at any of your algebra concept, then make sure you constantly review on those, because like really 95% of your calculus work is based on the algebra, right? And on top of that, the real calculus concept is just playing about 5% role. Right, so keep an eye on that. Right. Another one here, part B. Let's look at another equation equals 0. Okay. And just let's find both dy dx and dx dy. Okay. So we've got the equation. Find dy dx and find dx dy. Okay. So the dy dx first, and then once again I keep delivering that explanation already. So this time I'm gonna just get straight into the problem. Right. Our equation x cubed, there's a product between the x cubed and the y to the 5th, right? And minus a 4y, and then equal 0. So once again, I am going to differentiate or take the derivative both sides in respect to x. Okay? Differentiate that in respect to x. Just throw in with that differentiation, treating x as the main variable, treating x as a variable, and targeting y as a function. Okay? And so now in that way, right-hand side is easy, because no matter what it is, right, constant term come out 0. Easy enough there. So it's just the way how it is. We always tackle that with what's easiest, right, and then move up to the 1 and then save all of our remaining effort for the harder one to get. So now we got 2 terms. You guys follow it? Okay. So that means we have to do one separate differentiation on the x cubed times y to the 5th, and minus one differentiation work, right, for the 4y. So now, this one here is easier. What do you say? Equals 0 on the right-hand side. So just simply a 4 times some function of x, right? 4 times y being some implicit function of x. You guys follow it? And that's just taking the derivative there. So of course we have to leave the derivatives implicitly. So it's going to be something 4, right? The coefficient multiplied with some dy dx. That's it. Simple enough with that idea. And now let's handle this guy over here. So think about it. On scratch work, a little bit, right? On scratch work. It's a product, isn't it? X cubed times in product with y to the 5th, right? And we're learning this particular implicit differentiation technique after we already learned about what? The product rule and the quotient rules, right? So bring those in, because the product rule and the quotient rule and the chain rules are all, universal rules. Okay? And so far it's all the chain rule that massively being involved here. So let's now bring in the product rule for this, right? So differentiating, taking the derivative, right, in respect to x, that tells me what? Hey, the product rule says we're going to find one separate derivative on the x cubed. You guys with me there? Right. And then multiply with the other function being to the 5th power without the derivative. And then we add, right? We keep the x cubed, no prime this time, right? And we multiply with the derivative on the derivative of the y to the 5th. See what I mean? That's the setup right there. So that's sort of like on scratch work. So you guys keep it on scratch work. The formal work, I'm still leaving it incomplete right here, right? The formal step right here. So let's find out just what that is specifically. And so in that way, how I'm breaking it down right here, see? This part right here was already explicitly written in terms of x. So differentiating in respect to x, that's easy, right? That's just usual power rule. So 3x squared. So 3x squared multiplied with y to the 5th, as was stated here. But then the next term, x cubed, is left there without any change, right? The derivative here, we've done that tons of time now, right? This kind of work here, so it's making it what? 5y to the 4th power. That's the derivative of the outside, right? And we multiply with the derivative inside, simply being the implicit derivative. You guys would be there? And now I'm going to take that entire result, put that here in our formal step. So, see, because again, think of the y as some function of x. We just don't know what that is, right? So y to the 5th here means all of that to the 5th power. So there's outer, there's inner, right? there's the outer function, right? And there's the inner function. So taking the derivative in respect to x on the y to the fifth here. Yes, we take the prime, so that's why it's 5 times with the whole unknown function right there, the fourth, right? And multiply with the implicit f of x. And the implicit f of x is nothing but just dy dx. That's how I got it. So now I'm going to take that result, right? Put it all here in our formal step. So it's 3 x squared y to the fifth, right? Plus, and then let's clean up the terms a little bit. 5 x cubed y to the fourth dy dx. Ooh, I made it in that small space. Okay. So that's how we formally got our derivative coming out of this product. That's really the next step. Everything I've done there on the lower side of the board, that was just scratch work. You know, I'm about to take that out. And so in that way, so now we have, we're going to solve for dy dx specifically. So you got to understand, see, it was all due to the chain rule that says we multiply with the dy dx, we multiply it with the dy dx. And this term right here is free from dy dx, right? And it's a 0 on the other side. Bring that to the other side. So that's making it, so how about you guys are comfortable enough with algebra, allow me to do this. I'm going to combine two little steps in one. Do you notice a common factor between these two terms right there? Who's the common factor? The dy dx, right? The dy dx is a common factor. So I'm going to do this. 5x cubed y to the fourth minus 4. And factor out the dy dx. You guys see that? Okay, but then and at the same time I'm subtracting that term, right, to the other side. So all of that here is made equal to minus 3x squared y to the fifth. Still able to follow along? It's all the algebra at this point. I mean, we are done taking the derivative right at that step already. Okay? We're done taking the derivative, but now it's about to clean it up, right, and write that into one specific formula for the derivative. Okay? So it utilizes a lot of algebra right here. But now how do we solve for the dy dx? dy dx, we solve by, see, we're dividing both sides by this. 5x cubed y to the fourth minus 4. Dividing that both sides, right? Both sides. 5x cubed y to the fourth minus 4. So of course that cancels out, right? So that's why it leaves me dy dx to equals minus 3x squared y to the fifth, right? And we're dividing that here by 5x cubed y to the fourth minus 4. So we found our dy dx. And you see, before I'm moving on to, or maybe let me do the other route. So we found dy dx, but once again, the same equation there, the same equation we also asked to find dx dy, right? So let me now rewrite it. We got x cubed in product with y to the fifth, right? We're subtracting 4y, equal to 0. Everybody else following? So this time, let's take the derivative, both sides, but in respect to y, we're treating y as the variable. Okay? And we understand, right, that behind the scene, implicitly, x is some function of y. Right? X is implicitly some function of y. That's the key. Right? And then let's handle things from the easier side here. So the easier side is the right-hand side this time. Constant term, right? No matter what variable we're differentiating in respect to, it's come out 0. We've got two terms right here, so we can do dy on the x cubed y to the fifth. And we're subtracting dy on the 4y term. Right? Derivative rules, right? The basic rules, because the basic derivative rules allow me to separate it down to two separate terms together, right? Term by term, taking the derivative. And then once again, in my philosophy, we always tackle down the easier one first, right? Along the whole math right there. So this guy is easier. It's already explicitly defined in terms of y, right? So taking the derivative in respect to y, that's easy. Minus 4, right? Equals to 0. And then this, the some unknown derivative of the x cubed in product with x to the fifth. And we're about to tackle down that big word right there. Right? So let's find out what that is. I can just write it down right here. See, it's a product rule, right? We need the product rule here. So the product rule says we take the derivative individually on the x cubed, but make sure to multiply with y to the fifth with no derivative, right? And then we're moving on to adding, right? And then now I'm going to leave the x cubed the same. We multiply with the derivative in respect to y, right? For the y to the 5th power. And we subtract 4 from it. That makes that equal to 0. And so now also, actually this route right here is a little bit easier than the earlier one. So now right here, it's another easy derivative, right? It's already expressed explicitly in terms of y, right? And all we do here is take that derivative, so it's making it x to the cube right here, that remains the same, times 5y to the 4th. You guys agree with that? Okay. Minus 4, right, equals 0. What about that guy? We still have the y to the 5th remains right here, right? That x cubed, think of the x right here, the x itself is some unknown, some implicit function of x, function of y. So x cubed means some implicit function of y, but raised to the 3rd power, right? So taking that derivative, in respect to y on this x cubed right here means see, f of y, right? To the 3rd power. So chain rule says, see, there's outer functions, right? And there's the inner function right here. So chain rule says we go 3 times, right? The unknown function f of y raised to the power squared. So that's derivative of the outside function. Then we multiply with the unknown derivative, f prime of y, right? The implicit derivative. And so that part right here means what? It gives me a 3x squared, because that's here is an x, right? 3x squared times the x dy. So I'm going to take that result, put that right here. So we've got 3x squared, right? Times the x dy. Right? E product with the y to the 5th. Right, so really now my next step, I'm just going to rewrite the terms a little bit. So 3x squared, y to the 5th, right? Multiply with the x dy. The x dy, and we're adding with the 5x cubed y to the 4th, right? And subtracting 4, 0. So for this problem right here, this is the only term that comes with the derivative, the x dy, right? These guys are all independent from the derivative. So let's bring those to the other side then. Now I'm looking at 3x squared, y to the 5th. I'm so used to dy dx, but you see, there are times that it's dx dy. Using x and y for the variable is sometimes dangerous. 4 minus, right? 5x cubed y to the 4th. Good. Now I'm going to divide both sides by 3x squared y to the 5th. 3x squared y to the 5th. Right? That will make that the that bad habit. The x dy, right? We made equals 4 minus 5x cubed y to the 4th. Dividing that by 3x squared y to the 5th. Right. That's our final dx dy. See, so when I first introduced the implicit differentiation, I was using x squared plus y squared equals 4, right? And so anyone, and it's not just you guys here, it makes perfect sense that you're not so convinced that why we have to use implicit differentiation on something like this. See what I'm saying? Because we can easily solve for x in terms of y, or we can easily solve for y in terms of x, right? And then find the dy dx or the dx dy depending on what we want. But see, think about it. When you step into an equation like this, then solving for y in terms of x, is it really a good option? Because it's not that easy at all, right? To solve for y explicitly as a formula in terms of x. And then the other way around, it's not that simple to solve for x here in terms of y just to find a dx dy derivative like that. And that's why implicit differentiation is playing a good role in this kind of problem. It's being a good beneficial tool for us. All right. So let me bring in one more example just to find the dx dy or the dy and the dy dx actually. So now sine of xy minus 4 equals 0. So we got the product of x and y, right, inside of our sine function, inside of our trig function. You know what I'm saying? All right, so here's the thing. So let's find the y dx first. Sine of xy, right, minus 4 equals 0. I am going to differentiate both sides in respect to x. We want to find that first. This time is indicating it. So I want y as the function, but And on the other hand, I want x, right, as the variable. So x is the variable. So this equation, once again, in my philosophy, let's handle whichever the one that's easiest, right? This guy is so easy, so straightforward, comes out being what? 0. Another easy rule that we can apply, there are two terms. The sine of xy is one term, you guys following? -4 is the other term. So I'm going to separate it down to, let's find one separate derivative in respect to x on that sine of xy. We're holding on to that, right? But then subtracting the derivative in respect to x for the constant term 4. What's the derivative on the constant term again? 0, right? That goes to 0. So in my next step, the equation reduced down to just simply the differentiation in respect to x of sine of xy, right? -0, so we don't need to write it, right? And making it equal to 0. So things going pretty good, right? Things going pretty good. And I hope along the way that we keep cranking ourselves through the implicit differentiation. I hope the idea of the chain rule keep being reinforced, right? It's all about you recognize the inside and there's the outside here. Do you see some inside and outside with this setting? Who's the outside and who's the inside? The sign is the outside. The outside, yes.
X times y would be.
Yes, the whole product xy is the inside. You guys follow it? Right? So there's your inside right here. Right? That's your inside, and the sine function is playing the role of the outside. So now I ask you to recognize that for a reason, right? So chain rule says we're gonna, what's the derivative of sine function? Cosine, right? So the derivative of the outer function gives me cosine of the whole setup. xy stays in there. Okay, that's the derivative of the outside function. But we need to multiply with the derivative of the inside, which we haven't known yet. But it means differentiating the product x times y. Okay. You guys with me now? Right. And then making that all equal to 0. You see how we go with the chain rule right there? So the chain rule we keep being reinforced in these problems right here. Implicit differentiation is built on top of the chain rule. And so the cosine of xy is pretty much done. But now let's take care of what that is. But now it's just simply a product, right? A product of x, some function being x, and some function being implicit. So now we got what? I'm going to take the derivative in respect to x for that x, and then multiply with y with no prime, right? Product rule. And I'm adding with, now I'm leaving x out, right? No derivative, but I'm multiplying with dx on the y term. So now that gives me, so the cosine of xy is still here as a common factor outside of the parentheses. Well, what's the derivative of the function x right here? X, take the derivative, just 1. Okay. So that gives me just 1. Easy enough. Okay, 1 times y plus the x here was not differentiated. Differentiating in respect to x on that implicit function gives me nothing but just what? The dy dx, right? The famous dy dx. You guys following? Okay? Because we don't know what it is, so we leave that implicit. Equals 0. Okay. And so now we got the grouped in parentheses, in brackets, I mean, right? And then the cosine as a common factor. So let's distribute that, right? And solve for the dy dx. So I'm looking at now, so you multiply this cosine of xy to the y right here. We're looking at y, right, times the cosine of xy. Okay, that's one term. And then we're adding that to, see, I'm going to multiply that to that next term here, making it x times cosine of xy times the dy dx. Good with that then. And then making that equal to a 0. So in that case, in my next step, we're just solving for the dy dx, right? So I'm going to rewrite it as x times cosine of xy, right? dx, making that equal to the negative y times the cosine of xy. I was not so smart with the algebra for this problem. I could have just canceled that the cosine away from the earlier step, but it's still going to get us to the same answer. I didn't cancel that earlier, so I could. So now I can cancel it here. I could have done that the other way around. multiplying both sides by x, right? And we're solving for y dx here. So we got, see, in this expression right here, let's just run it one more time. So the cosine got canceled away, right? So now we're left behind with a very simple derivative, dy dx comes out here with minus y over x. Are we good? Okay. And what I said about not being smart at me today is just like right at that step right here. Right at that step right here, I could have saved myself some effort by just canceling out that cosine already, right? Without distributing it. You see what I mean? So learn from that lesson right there, from that the mistake of mine. So in the future, I mean, if you could, right, cancel, because it's a 0 on the right hand side already, right? So dividing both sides by the cosine of x, making it a lot more reduced. Just y plus x dy dx equals 0, right? And then we solve for the dy dx a lot more easily. So that's how we do it in the dy dx. So what about the dx dy? Would be the crazy amount of so we've got sine of xy at start, right? Minus a 4, okay, making it equal to 0. Right? We want to differentiate that in respect to y, that's right? And we've done quite a few of those, so allow me to start speeding up the step a little bit. So right hand side gives you a 0. Left hand side, we can break it down. It's pretty same work that we've done. One separate derivative on the sine of xy, right? Subtract this separate derivative for the 4 in respect to y. So in my next step, yes, there's the 0 on the right hand side. Derivative for that term, no matter if it's in terms of x or in terms of y, so you're taking the derivative of a constant, you know, 0 minus 0. That one right here, see, the chain rule kicks in again, right? No matter what variable we're doing, but there's always the outside being the sine function and the product xy being the inside function. So we got cosine of xy, right? That's the outside derivative, right? We multiply with the derivative, the differentiation in respect to y for the xy. You guys good with me on that? So really it reduces down to cosine of xy, right, times the differentiation of xy all equal to 0. So keeping the cosine xy here. Now, product rule says, now this time just be careful, we're treating y as a variable, right? And so product rule says I'm going to take the derivative of x in respect to y, keeping in mind this time that x is some function of y. So we take that derivative, multiply with y without derivative. We adding that to, now I'm going to leave x without derivative. I'm going to multiply with the derivative just of the y equal to 0. And then just right from here, you guys realize just like my mistake, I've learned from my own mistake earlier. I mean, it's not really a mistake, but this can be a lot more efficient. Cancel both sides with the cosine of xy, right? Divide the cosine of xy from both sides. Because it's a 0 on the right hand side, right? And then it's a product between the cosine of xy with this whole mess right here. So in my next step, really, I'm having what? There's no more cosine of x. I mean, no more cosine of xy. This terms here reduced down to just simply a. See, what's the derivative for? I mean, the derivative of y in respect to y, which is 1. So we got 1, right? Plus, which is all equal to 0 here. This term here gives me, see, x here is the implicit function. So taking the derivative of an implicit function, we just have to leave that as a dx and dy. So I have y times dx and dy, right? Plus 1 equals 0. Actually, I'm missing a term here. It's supposed to be plus x. It's 1 times x, right? X. So now that means solving for dx, dy, we're looking at subtracting that to the other side, minus x, right, over y. That's how it's done.